Hello everyone, this is the third video in a series discussing how Seisnetics can be used to screen CCS reservoir candidates. So in the first video we saw how we could do seismic QC, comparing images. In the second video we worked on the SMEAIA dataset from offshore Norway to quickly extract and display all the surfaces, the faults, and identify some of the key components of a good CCS site. So this one was a caprock. And in this third video, I will run the same analysis, but just to show you that it works for much bigger datasets and even merge. So the idea here was to run on the dataset from offshore Texas, so in the Gulf of Mexico, an area which is also considered for CCS. So I will start by displaying the seismic. So here an inline. I have already changed a little bit the raster range, so we can have an idea, we can really see the reflector better. And so now you see that's the kind of configuration we have. So complex geology with a lot of faults, district faults included. And so the first step, once again, was to extract all the surfaces. So I'm just opening the geopopulation. So this dataset is a 20 gigabyte. And I am displaying, once again, all the surfaces, starting by monochrome, to have a look at the results of extraction. So this might take again a couple of seconds because I'm running on a simple laptop and this is quite a nice data set with thousands of surfaces. So now I have all my surfaces, so we can clearly see that it's done a very nice job extracting everything. And I can move again along the volume to have a look at the context, geological context, the faults, the geometry, some boundaries. So this is a very nice data set. So the extraction of horizons here on this took less than an hour on the larger machine. And so what I can do now also is to display in polychrome using the fitness. So we saw in the second video that the fitness was the seismic features variability. So something interesting for CCS, of course, is you are looking for caprocks, which should have a quite homogeneous seismic features. So now the idea is to identify the zone which have, I would say, some unique color, so homogeneous color, like light green, for instance. So you see you have a few areas in the dataset where you have a horizon that can really be tracked over large surfaces that could be interesting. So again, doesn't mean that it's because it's green, it's a caprock. It's just something which is rather homogeneous, but at least that's a good start. So if I zoom in a little bit, then we can see that there are a couple of horizons here, especially on the top, that look quite interesting. So I'm just going to take a couple. So for instance, these 2 or 3 here, to have a look at the results of extraction. So here I have 1, 2, 3, 4, 5, and 6. So for instance, on this side of the fault, we see that some things are rather appear homogeneous, but it's way more complex than it seems when you look at the data. So something I wanted to point out also on this dataset is if I look, for instance, at the larger surfaces, here we see some nice channels, yes, in this area. So we see that there are quite a few lateral variations in the surfaces. So I will try to take an example which might be even way more interesting in that case. So it looks like some of these volumes have been merged. So the idea is it's unclear if it's just one volume or there are several, because things appear sometimes, the geometry is a bit strange. So the idea is there might have been here some clear merges between different seismic volumes. So anyway, let's come back to our horizons. So I discussed how we can have a look and identify the zones of interest by looking at the seismic features variability. But the more interesting, of course, in this dataset are the faults, because there is quite a few. And so here the extraction of the faults took 25 minutes, so extraction of polygons. And then you can decide to either build everything automatically or in an assisted way. So the assisted way will just be, like I showed in second video, extracting faults crossing a couple of horizons, or all of them at once. So that's the result of extraction. So here I'm just displaying the polygons in 2D. And so we can clearly see that it also did a very nice job with the extraction of fault polygons in this area. So there might be some places where you need some local help because basically the seismic and the boundaries are not clearly visible, since it needs, I mean, to have some horizons to work. Then you might have to help it basically to merge these two guys together, assuming that this is the same fault, of course. So, but that's an idea, and I will show now the surfaces, the polygons, sorry, in 3D. So we can clearly see the very nice geometries of the faults already. So some polygons line up very, very well. So what I can do also is just try to display maybe the longest fault polygons. So here you see the largest one that can be seen very well. So you see, for instance, here we can basically help it just to catch the last one, the Listric faults. It's really based here on the seismic quality. It's done a much better job on the other side of the seismic. So that's an idea here. We can track it very well. And so, of course, I have done already the job, but you can compute all the faults now, the fault planes directly by just, I can do it once again, for instance. I can delete all the faults, the work I've done. So first they will be displayed, so we can have a look at them. And then I will delete everything and start again the process. So you can have an idea about how fast these things are. So here I have done that, so I will delete them. Yes, I want to delete. So I'm removing all my faults. But of course, I keep the polygons. So the idea would be just to extract a couple of them to show the process of fault construction, even for large datasets. Because again, in Seisnetics, you have either the possibility to run manual extraction, so you just click and build fault sticks, and then you will have automatic interpolation. Then you have the assisted, so you will select a couple of polygons, and then Seisnetics will build the polygons tracking the other ones in the dataset that could be brought to build a coherent plane. Or you have the direct and automatic approach, the one I use to build the dataset that you see on the screen now, which is you just one click and you let it run until it has built all the fault planes. So these are the different options. So I don't know how many faults I have here, but it's taking some time to delete for sure. Okay, there we are. So now all the faults have been deleted, and what I'd like to show you is how we can build automatically a couple of faults, not running the full process because the dataset is large and it might take 20 minutes just to extract all of these guys. So for instance, let's say that I want to extract and to build the plane for this little fault here. So I can just create a fault, give it an orientation. I say, okay, I want you to extract and to build this fault. So up, you see, I built the fault there. So this is how fast these things can be done. And of course, you can run this for all the faults. You can also decide that you want to build a fault on your own and just maybe one of them. So for instance, let's build another one using the assisted tool. You say that you just want to build this one, for instance. So now I just I've guided a little bit Seisnetics, and it will build the fault plane using the polygons in the area. So now you see I have two polygons, the one I built before, and I have this plane now. So this is how fast you can basically help and guide the tool to have a very quick extraction of all the fault planes in any volume, and start screening your site and your area for possible CCS reservoir candidates. This is the end of this third video, and in the next one we will discuss time-lapse analysis.